Hello students, welcome to EPG Pathsala. I am Professor D. Vel Murugan, the University Grants Commission Basic Scientific Research Faculty from Center of Advanced Study in Crystallography and Biophysics, University of Madras, Gindi Campus, Chennai. Today we are going to talk on topics reciprocal space, reciprocal lattice and Bragg's law in paper Biocrystallography. So students, let us see what we are going to learn in this model today. We are going to first know about reciprocal space. What is reciprocal space? Why it is called reciprocal? Because there is one space known as real space in which the unit cell dimensions are defined like A, B, C. Whereas in reciprocal space, it is inverse relation. A star, B star, C star, and the three angles are alpha star, beta star and gamma star. So depending upon the 7 crystal systems, we have different relations between these real space lattice vectors and the reciprocal space lattice vectors. Now, this reciprocal lattice also we are going to see in detail. This is a concept introduced to visualize the Bragg's law mainly. Then we are going to see what will be the angles between the Bravais lattice planes. And finally, we are going to have the derivation of Bragg's law. The reciprocal lattice was introduced by Professor Ewald in the year 1921. If little a, b, c represent the elementary translations of a space lattice, which is also called a direct lattice, we can define another lattice, a second lattice, which is reciprocal to the first one. That is why this new lattice is known as the reciprocal lattice. And this reciprocal lattice is defined by the translations A star, B star and C star such that A star is normal to the plane BC and B star is normal to the plane containing the direct lattice vectors A and C, and C star is normal to the plane containing the direct lattice vectors A and B. So similarly, the real space volume and reciprocal space volume are also related. V star will be 1 by V. Now, the reciprocal of the reciprocal lattice is the direct lattice, and the consequence of X-ray diffraction can be understood in an elegant way if one is clear about the reciprocal space concept. That is the beauty of reciprocal space concept. We are going to see that whenever crystal rotates, the reciprocal lattice also moves along with it, and whenever it cuts the sphere of reflection, then that point satisfies Bragg's law. It's a very simple concept and so on. Let us understand what is meant by reciprocal space. In a crystal, the atoms form a periodic array and the corresponding diffracting pattern will also be a regular array of spots, and they form the reciprocal lattice in the reciprocal space. If the diffracting atoms are more widely spaced, the diffraction spots get closer. When atoms get closer in one direction only, the reciprocal lattice will expand in that direction only. If other atoms are added without changing the crystal periodicity, the position of the earlier spots will remain unchanged, but their intensities will vary. The measurement of reciprocal lattice using crystallographic techniques allows to determine the organization of atoms in molecules or in solids. One can refer to figure 4.1. In figure 4.1, we have two sets of figures. One shows the real space, the other shows the reciprocal space. First of all, let us see. In the real space, these dots, these form lattices. Whatever lattice means, in a crystal earlier, crystals made up of unit cells, and in the unit cells molecules are there. And these unit cells have the three-dimensional periodicity. They are adjacent to one another in all the three directions. Now if we replace each unit cell as a point, then we get the formation of a lattice. The lattice plus the motif, that unit cell, gives you the entire crystal. So this is understanding. Now if you look at the real space, separation of the spots along the horizontal direction are larger compared to the separation of spots in the vertical direction. But if you look into the reciprocal space, the separation of spots in the horizontal directions are smaller than the separation of spots in the vertical direction. This is what I mean by reciprocal space. In the real space, the separation between the spot is larger than in the reciprocal space, though smaller. If they are smaller in the real space separation, then in the reciprocal space it will be larger. It's quite clearly seen from the figure. Let us understand what do you mean by a reciprocal lattice. During the stereographic projection, the morphology of a crystal can be represented by a bundle of lines drawn from a point normal to the faces of the crystal, but this description lacks media dimensions. If each normal is given a length that is inversely proportional to the corresponding interpacing in the real lattice, the lattice so formed is called a reciprocal lattice. Bravais lattice can be described by three non-coplanar vectors A, B, C representing the unit cell edges in the real space, which is clearly shown in the figure 4.2, which we will see later. Every crystal has a lattice as its geometric basis. The lattice is described as a regular, infinite arrangement of points in which every point has the same environment as any other point in 1, 2 and 3-dimensional space. The unit cell of a reciprocal space is described by three vectors A star, B star and C star. The reciprocal lattice vectors A star, B star, C star can be related to the direct basis vectors in the real space, which are A, B, C, by the relations given in 4.1, namely A star equals B cross C over V, B star equals C cross A over V and C star equals A cross B over V, where V is the volume of the unit cell given by V equals A dot B cross C. B cross C is a cross product of vectors B and C, which will be a vector, but A dot B cross C will be a scalar, giving you the value of the volume V. So one you can refer to figure 4.2. Here you can easily see that A star can be given by the area of OBGC over V, which is equal to 1 over OP, where OP is the perpendicular from the origin O of the Bravais unit cell to the plane ADFE containing the point P. Similarly, OQ is a perpendicular from the origin O of the Bravais unit cell to the plane DBGF, which contains the point Q, and OR is a perpendicular drawn from the origin O to the plane EFGC containing a point R. Figure 4.2 shows the unit cell in the real space and also the coordinates obtained in the reciprocal space. It also shows you what do you mean by the reciprocal lattice vectors A star, B star and C star, which you have recently seen. So we have seen that OP is perpendicular to the face OBGC and it is moving towards ADFE and so on. From the figure and from the definition of these reciprocal lattice vectors in the real space and reciprocal space, one can easily infer that A dot A star will be equal to B dot B star will be equal to C dot C star, which will be equal to 1 as given by 4.2, and A dot B star equals A dot C star equals A star dot B, which will be equal to 0 as given by equation 4.3. Equation 4.2 gives the interplanar spacing D star of HKL in reciprocal lattice. Because you know A star, B star and C star are the cell edges of the reciprocal lattice, which have been related to the ABC, the cell edges of the real space lattice. D star of HKL is simply HA star plus KB star plus LC star. It has to be noted that in a unit cell of Bravais lattice, the vector R from the origin to the point x, y, z in the unit cell is in general given by R equals xa plus yb plus zc, where a, b, c are the cell dimensions of the unit cell in the real space. This is given by equation 4.5. Already we have given an expression for D star HKL as HA star plus KB star plus LC star as given in equation 4.4, and the expression for the vector R is also given in equation 4.5 as R equals XA plus YB plus ZC. Then simply the scalar product D star of HKL dot R will lead to the equation of the plane in Bravais lattice normal to the direction of D star of HKL. This equation is simply Hx plus Ky plus Lz equals a constant kappa. So figure 4.3 shows two planes which are defined as kappa equal to 0 and kappa equal to 1. We will describe this in detail in the next projection. When kappa equals 0, the plane passes through the origin. When kappa equals 1, this is called the first plane from the origin to the family of HKL planes. You can refer to this figure. Since the fractional coordinate x equals the actual intercept divided by the original cell dimension a, which is equal to capital X by a, and like that y equals capital Y by b, and z equals capital Z by c, where these little a, b, c are the cell dimension in the real space. Now these little x, little y, z are called the fractional coordinates. We can write the above equation hx plus ky plus lz equal to a constant kappa as h times capital X by a plus k times capital Y by b plus l times capital Z by c, where we have simply substituted for the fractional coordinate little x, little y and little z by the above expressions. Now this capital X, capital Y, capital Z are crystallographic axes, and little a, b, c are the corresponding intercepts made by the parametral plane. Referring to equation 4.2, since capital D is the foot of the perpendicular from O, and also since it lies in the same plane as P, the termination of R from the same point O, it follows that D star of HKL dot D of HKL will be equal to 1, or in other words, D star of HKL is nothing but 1 by D of HKL. That is why it is known as reciprocal lattice vector, because 1 over DHKL. So DHKL is the real space, so D star HKL is the reciprocal space as given by 4.6. Thus any point HKL at any point of lattice is said to correspond to a family of planes HKL, or a mirror plane, a mirror indices plane in the Bravais lattice with interplanar spacing D of HKL. If capital P is a Bravais lattice point, and if vectors capital U, V, W are the coordinates of the Bravais lattice point, then the position vector can also be written in terms of this U, V, W as R vector equal U times A vector plus V times B vector plus W times C vector. Again, these little a, little b, little c vectors belong to the reciprocal, not real space vectors, which is given in 4.7. Then the scalar product D star of HKL dot R can be written, because we know D star equals HA star plus KB star plus LC star. This A star, B star, C star belong to the reciprocal space, because A, B, C belong to the real space. So now we can easily take a dot product of D star with R. So to get you HU plus KV plus LW, which will be simply kappa, where we made use of equation 4.2 and 4.3. So this is a new equation 4.8. The coordinates U, V and W describe the direction or the directed line, and you represent this within a square bracket U, V, W. In the reciprocal lattice, V star is defined as A star cross B star dot C star as given in 4.9. Substituting equation 4.1 in the above equation for this A star, B star and C star, we get V star as 1 by V cube times B cross C cross C cross A dot A cross B, which can be finally simplified as V star equals 1 by V. So V is a volume in the real space. V star is called volume in the reciprocal space because V star equals 1 by V as given by equation 4.1 and V star equals 1. Now we can derive a formula for the angles between Bravais lattice planes. For that you have to look into figure 4.4. Here H1K1L1 and H2K2L2 represent the two planes. Then the angle between these two planes phi may be obtained from the supplement of the angle between the corresponding reciprocal lattice vectors. So d star of H1K1L1 dot d star of H2K2L2 is simply minus d star of H1K1L1 times d star of H2K2L2 times cosine of the angle phi. This is equation 4.11. You know, phi is marked here. The two planes are also marked. D star also marked in the figure 4.4. Now we have to know the relation between direct and reciprocal lattice parameters. So let us see the angle relationship. If alpha, beta, gamma are the angles in the real space, then the corresponding angles in the reciprocal date alpha star, beta star and gamma star are given by alpha star equal to 180 degree minus alpha, beta star equal to 180 degree minus beta and gamma star equal to 180 degree minus gamma. Already we have seen that V is the volume of the unit cell, and if V star is the volume of the reciprocal space of the unit cell, then V star equal to 1 by V. This V is nothing but A times B times C square root of 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. Thus the volume of the unit cell can be calculated if you know the 3 cell edges and the 3 angles each opposite to one of these axes. Let us consider a triclinic system. So here we have the formulae for A star, B star, C star, cos alpha star, cos beta star and cos gamma star. A star will be simply 1 by A sin beta sin gamma star, which can also be written as 1 by A sin beta star sin gamma. B star will be 1 by B sin gamma sin alpha star, which is also equal to 1 over B sin gamma star sin alpha, and C star equals 1 by C sin alpha sin beta star, which can also be written as 1 over C sin alpha star sin beta. Cos alpha star equals cos beta cos gamma minus cos alpha over sin beta sin gamma. Cos beta star equals cos gamma cos alpha minus cos beta over sin gamma sin alpha. Cos gamma star equals cos alpha cos beta minus cos gamma over sin alpha sin beta. Similarly, cos alpha equals cos beta star cos gamma star minus cos alpha star over sin beta star sin gamma star. Cos beta equals cos gamma star cos alpha star minus cos beta star over sin gamma star sin alpha star, and cos gamma equals cos alpha star cos beta star minus cos gamma star over sin alpha star sin beta star. The above are the relations between the reciprocal lattice parameters and the Bravais lattice parameters. Using the above formula for A, B, C, A star, B star, C star and so on, the value of D, the distance between adjacent planes in the set HKL planes, may be found from the following equations for the different crystal systems. In case of cubic system, we have the formula 1 by D square equals H square plus K square plus L square over A square. In the case of tetragonal system, we have 1 by D square equals H square plus K square over A square plus L square over C square. In case of hexagonal, we have 1 by D square equals 4 by 3 times H square plus HK plus K square over A square plus L square over C square. In case of rhombahedral, we have 1 by D star equals H square plus K square plus L square times sin square alpha plus twice HK plus KL plus HL times cos square alpha minus cos alpha over A square times 1 minus 3 cos square alpha plus 2 cos cube alpha. Again, the distance between the lattice planes in the remaining 4 crystal system can also be given as 1 by D square equals H square over A square plus K square over B square plus L square over C square for the orthodromic system. For the monoclinic system, 1 by d square equals 1 by sine square beta times h square over a square plus k square sine square beta over b square plus L square by C square minus 2HL cos beta over AC. In triclinic, 1 by D square equals 1 by V square times B square C square sin square alpha H square plus A square C square sin square beta K square plus A square B square sin square gamma L square plus 2AB C square cos alpha cos beta minus cos gamma times HK plus 2A square BC times cos beta cos gamma minus cos alpha times KL plus 2AB square C times cos gamma cos alpha minus cos beta times HL. In the monoclinic system, it takes simple values. A star is simply 1 by A sin beta, B star is 1 by beta, C star is 1 by C sin beta, alpha star equals alpha equal to 90 degree, beta star equal to 180 degree minus beta, and gamma star equals gamma equals 90 degree. Now we have an important derivation, Bragg's law. If one has to look at the figure, we have shown two planes PQ and P prime Q prime in figure 4.5. So these are the two lattice planes with interplanar spacing, the perpendicular distance between them as little d, which we mean d of HKL. Now if we consider the left hand side, AB is the first incident ray and after diffraction it goes along BC. This is known as scattered ray also. The angle of incidence, angle ABP, is nothing but theta. Now, A prime B prime is the second ray incident on the second plane P prime Q prime with an angle of incidence A prime B prime P prime as theta. Now, B prime C prime is a diffracted or scattered ray from the plane P prime Q prime. The first ray travels a total path of AB plus BC and the second ray travels a total path of A prime B prime plus B prime C prime. Now we are interested in calculating the path difference between the two rays. So to do that, you drop a perpendicular from point B to A prime B prime touching it at D and perpendicular to B prime C prime touching it at E. So these are also called the foot of the perpendiculars. Dear students, now we are going to see the geometrical proof for Bragg's law. It's a simple mathematics only. So already we have seen there are two planes with a separation called interplanar distance d, and there is an incident ray. Two rays are incident, one on the first plane and another on the second plane, and these are getting diffracted again into from the planes, the first and second plane. Now let us consider the ray A prime B prime. This A prime B prime can be written as A prime D plus DB prime. But you know already A prime D is AB. So hence your A prime B prime plus A prime D will be simply A prime B prime minus AB, which is equal to DB prime. Similarly, your B prime C prime will be equals B prime E plus EC prime. But if you look at the figure, you see that EC prime equals BC. Therefore, B prime C prime minus BC equals B prime C prime minus EC prime, which is simply B prime E. So now we have the relation for the total path difference. What is the total path difference? A prime B prime plus B prime C prime minus AB plus BC. Now which is simply A prime B prime minus AB plus B prime C prime minus BC, which is simply DB prime plus B prime E. But if you look at the angle DB prime B, this is simply 90 minus theta. And in the right angle triangle BDB prime, angle BDB prime equals 90 degree. Hence angle B prime BD equals theta. Similarly, if you look into the figure, in the triangle B prime EB, the angle B prime BE is also theta. So now the two triangles BDB prime and BEB prime are right angle triangles with hypotenuse BB prime, which will be DHKL, and DB prime, which is again DHKL sin theta, and B prime E, which is equal to DHKL sin theta. Hence, the total path difference between the two rays during the diffraction is equal to dB prime plus B prime E, which is equal to DHKL sin theta plus again DHKL sin theta, equaling to 2 DHKL sin theta. The incident rays are from X-ray waves, and similarly is true for the diffracted rays also. So the total path difference 2D sin theta for diffraction maximum should be integral multiples of wavelength. So 2D sin theta equals n lambda, that is the famous Bragg's law. We have seen from figure 4.5 that the diffracted rays go along the direction BC and B prime C prime. Only when these waves interfere or superpose constructively, that is, when the phase differences are integral multiples of 2 pi, or the path difference, as we have seen the derivation, is integral multiples of lambda, that is n lambda, where n is an integer, the diffraction maximum will occur. In other words, now we have obtained the condition for diffraction maxima as 2 DHKL sin theta equal to n lambda. This is your famous Bragg's law, for which Nobel Prize has been shared between the father Henry Bragg and the son Lawrence Bragg. So students, now let us summarize what we have learned in this module today. We have understood the reciprocal space and the reciprocal lattice concepts, which eventually simplify the interpretation of the diffraction experiments. As I told you in the beginning, reciprocal space was introduced for easier understanding or visualization of the diffraction phenomena. Again, if you imagine reciprocal space, then as I told you repeatedly, whenever a crystal rotates, the reciprocal lattice also rotates along with that. And we have constructed a sphere known as Ewald sphere, where the radius of the sphere is 1 over lambda, and this reciprocal lattice, whenever it cuts the sphere of reflection, then that point obeys Bragg's law. So like that is easier visualization. And also you must know why it is called reciprocal lattice. If you look at the formula, the distance will be reciprocal of the original distance, 1 by d. So d will be an angstrom, 1 by d is the reciprocal of d. That is why it is known as reciprocal lattice, defined in reciprocal space. Now, the relations between reciprocal lattice parameters and the Bravais lattice parameters are also determined. When I say Bravais lattice parameters, that is generally your cell diamond constant A, B, C and the 3 angles alpha, beta, gamma. When you talk about reciprocal lattice, now this is defined by A star, B star, C star and alpha star, beta star and gamma star. Already we have seen the relations between these 6 parameters in the Bravais lattice and also in the reciprocal lattice. Now, the value of the interplanar spacing D has also been studied for different crystal systems. We have given the formula for the 7 crystal systems for the DHKL, and finally we have also given the proof for Bragg's law. So this is the end of the module. Thanks for listening to me.